We're going to continue our study of how to find the integrals of products, but we're going to focus on the product of trig functions. And so the number one thing that's going to come in handy when you're doing this is using your identities and appropriate substitutions. So let's start, and today we're going to focus on just sine and cosine. So say I find the sine, the integral of sine cubed x times cosine x. So if I let sine equal my u, then derivative of sine will be cosine. And so I can replace u with sine of x with u, and my cosines will cancel out, and this just becomes basically integral of u cubed du, which we all know to be 1/4 u to the 4th plus c, or we rewrite that as 1/4 sine to the 4th of x plus c. Now that's basically easy, but sometimes it gets more hard. So let's remind some trig identities you learned in trig class. The Pythagorean theorem we know is sine squared x plus cosine squared equals 1. We also know that sine squared x is equal to 1 minus cosine of 2x over 2, power reduction formula, or cosine squared is equal to 1 plus cosine of 2x divided by 2, again, power reduction formula. Okay, so we're going to learn some techniques. It all depends on the degree of that sine is raised to or the degree that cosine is raised to. So basically our general strategy, anytime we have the integral of a sine to some power times a cosine to some power, are as follows, where either n or m are odd functions. So our first one is if the cosine function is the odd function. So if cosine is odd, you're going to let u equal your sine function. And so the derivative of that sine function will be a cosine function, will be cosine of x dx. And so that's going to cancel out one of our cosine functions. Then we'll have a leftover even amount of cosine functions, which we will then turn into terms of sine using the Pythagorean identity, where we solve for cosine squared. And in Pythagorean identity, we know cosine squared is equal to 1 minus sine squared. Okay, so here in this example, we're going to find the integral of sine squared x times cosine cubed x dx. So since cosine is an odd power, I'm going to let u equal sine of x. So the derivative of sine of x is cosine of x. And so when I do my u substitution, I end up with the integral of u squared times cosine cubed x. And replace the dx with du over cosine of x. Now one of my cosines cancel out my cosine cubed x. It leaves me with cosine squared. Then I'm going to replace this cosine squared with 1 minus sine squared, or 1 minus u squared. So I have u squared times 1 minus u squared du, which is simply the integral of u squared minus u to the 4th du, which is something we can easily integrate and use our power rule. So I get 1/3 u to the x, u cubed. So I get 1/3 u cubed minus 1/5 u to the 5th plus c. So now I have to go back to my original function, substituting in sine of x in place of every u to get 1/3 sine cubed x minus 1/5 sine to the 5th x plus c. And that's how we integrate products when the cosine function is odd and we're multiplying by a sine function. Now if the power of the sine function is the odd, we will make u equal to cosine of x. And so du is going to be equal to negative sine of x dx. And the remaining even functions of the sine may be converted to cosines using, again, the Pythagorean identity, where sine squared of x is equal to 1 minus cosine squared x. So here we're going to evaluate the integral of sine cubed x cosine to the 4th x dx. So since my sine function is the odd, I'm going to let u equal my cosine function. So that means the derivative of u is negative sine x dx. So substituting back into the original problem, I got the integral of my sine cubed x times u to the 4th times, we place in dx with du over negative sine. So one of those signs cancel out with the other sign, and I'm left with sine squared x times u to the 4th, and we have that negative du. Factoring out the negative, replacing that sine squared with 1 minus cosine squared. and replacing cosine squared or cosine with u, I end up that we have negative the integral of 1 minus u squared times u to the fourth, which is simply negative the integral of u to the fourth minus u to the sixth du. And now we just integrate. So I end up, when I go back and substitute in place of u, cosine of x, I get my answer as negative cosine to the fifth x over 5 plus, because don't forget to distribute that negative on the outside, plus cosine to the seventh of x over 7 plus c. Okay, our third situation is if the powers are both, the powers of the sine function and the cosine are all even. So we have no negative exponents. Okay, we're going to make repeated use of our identities. And this is where you might need to use your power reduction identities and replacing sine squared x with 1 minus cosine of 2x over 2, or the cosine squared of x with 1 plus cosine of 2x over 2, so that we can convert these all into odd powers of cosine. So everything's going to be converted into cosine. And then we would evaluate it. So here we have cosine to the fourth x dx. So we can think of one of our functions as 1, and the other function is cosine to the fourth x. That's an even power. Okay, we have the integral of cosine to the 4x, and now let's break that up to cosine squared x times cosine squared x, since our degree is an even power, and it's our only trig function here. Now, I couldn't do just straight u substitution, because then if I made my u cosine, my derivative of cosine is sine. I can't cancel that out with anything. So this is the reason why I got to do some trig formulas here. Now we're going to replace each of these cosine squared of x with our power reduction formulas, which is the 1 plus cosine of 2x over 2. Now to make this a little bit easier to work with, I'm going to get rid of the compound, I'll get rid of the fraction here, and I'm just going to rewrite this, each of these fractions as 1/2 plus 1/2 cosine of 2x. Okay, now we're going to use our full method to multiply these two products together, which is going to give us 1/4 plus cosine of 2x over 2 plus cosine squared of 2x over 4 dx. Now the first two terms are ready to integrate, but the second term, I have a cosine squared of 2x, and so I need to do the power reduction formula again in this last term, so I can get down to a single power of cosine. So in this last term, I'm going to replace that cosine squared of 2x with 1 plus cosine. Now I'm going to double that 2x, makes it a 4x angle over 2. And so now my integral is finally simplified down to 1/4 plus that 1/2 cosine of 2x plus a 1/8 plus a 1/8 cosine of 4x dx. Oh, and let's go ahead and combine that 1/4 and 1/8 together. So we have the integral, when I combine the 1/4 and the 1/8, my like terms, end up with 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x dx. And now we're ready to integrate. So the integral of 3/8 is simply 3/8 x plus, now the integral of 1/2 cosine of 2x, I'm going to make my u 2x. And so when I integrate that, I'm going to end up with 1/4 sine of 2x. And then the last term, my u is now 4x. So that ends up being 1 over 32 sine of 4x plus c. Whew. And that's an example of when it's odd, when you don't have any odd powers and you have only even powers of sine and cosine. For this number 5, notice this is the same problem as we just did in problem number 4, except now it's a definite integral. So I'm just going to copy down my answer I got from the last problem, which was 3/8 x plus sine of 2x divided by 4 plus sine to the 4x divided by 32. And I'm going to evaluate this from 0 to pi over 2. All right, start by plugging in our pi. Well, I end up with 3 pi over 16 plus 0. And then we got to figure out plus 0 minus, now plugging in 0 gives us 0, minus 0 plus 0. Well, my answer is just 3 pi over 16. Note that the only term that contributed to our solution in this problem was at 3x over 8. So Wallace's formula helps us kind of make some predictions like this. Okay, so the Wallace's formula, if I do in the integral from 0 to pi over 4 of a cosine to an odd power dx, and the odd power is greater than 3, my formula is going to be 2/3 times 4 to the 6 times 6 to the 7. So notice my numerator term is counting by even numbers. My denominator term is counting by odd numbers. Now, our second situation, if n is even, which it was in our example number 5, and n is greater than 2, then the integral from 0 to pi over 2 of cosine to an even power of x dx is equal to 1/2 times 3/4 times 5/6 ... So this time the numerators are odd numbers starting at 1, and then denominators are even numbers starting at 2. And then you answer, and then you're going to multiply your answer by pi over 2. I forgot to write that on the top one. So here, notice that my n is 4. So if I was to have you work problem number 5 using Wallace's formula, because it's integral from 0 to pi over 4, I'd say, okay, n is, okay, so notice in this situation, I always start at 1 over 2, 3 over 4, and I keep going until I get to the numerator is going to be 1 less than my power of my n. And then since n was 4 in this problem, my numerator is 3. And I'm going to go until my denominator is equal to my n, which is 4. So I did 1/2 times 3/4 stop, and then I times that by pi over 2. And then 1 times 3 times pi gives us 3 pi. 2 times 4 times 2 is 16. So we get our answer of 3 pi over 16. So there's 2 ways to do that.